All right, welcome to Unit 3. Energy and Society is the title of this particular unit. The first topic that we're going to look at is work and energy. So what's the goal today? I can identify energy issues that exist and can articulate the connection between issues and work and energy. Quite a mouthful. So some of the energy issues, usually we do a bit of a brainstorming session here, so I'll rattle off a couple that we kind of run into. In our local area, probably one of the biggest issues in terms of energy is the wind turbines. Okay, a very hot topic right now, and no real clear-cut decision or winner as to which way it's going to go. Worldwide, you have issues such as coal power, nuclear is an issue. Lots of energy, but there's also a fairly large negative with it. Same with the coal power. You get into gas plants. So gas power, another local issue that's a hot topic at this point in time. Then you move into hydroelectric. And that would be something like Niagara Falls, for example. And then the whole creating dams in order for energy generation. So some of the issues you run into is water and wildlife management issues. And why is it such an important topic? Well, we need enough energy to run our electronics. If we don't have electricity, your computers, your iPads, your iPods, your tablets, they're not going to work. So energy to run electronics, which leads us into shortages, brownouts, blackouts, etc., etc., renewable resources, and so on and so forth. So you can see that this massive, and I could keep going here. This is just rattling stuff off in under 2 minutes. It really is. It's a regional thing with some respects. The wind turbines is a very regional thing right now for us. Coal, nuclear, and gas power is more of a global issue. Hydroelectric, it depends where you are. In Quebec, it's a hot topic. And the whole reason for this big push, or why is it such a forefront, is it's never going to go away because we always need energy to run all our electronics in our everyday life. So very, very important here. And we're just going to scratch the surface because really my only focus here, we're going to investigate, we're going to talk about this quite a bit because it is a local issue. It hits home for a lot of people in the area. And then we're going to talk about the calculations on electronics and stuff like that, and talk about the shortages and how it all works together. All right, so we're just going to really scratch the surface here and kind of give you a chance to think and talk about some of the stuff related to energy issues. So a couple of definitions that we're going to run through here, and we'll write them up. So energy, definition for it, is the ability to do work. The ability to do work. And work then is the transfer of one form of energy, I should say, one form of energy to another. Now, just as a heads up, as you move through this unit, work and mechanical energy are really synonymous. They really mean the same thing, especially with the book that we use. So mechanical energy. So if you see the term mechanical energy, it just means it's another form of work or a specific form of work. So energy transfer. Often we look at how is energy being transferred to one form or another. So I'm just going to give you a quick example here, and let's look at the car. What energy transfers are we really looking at? Well, where does energy come from in the car? It all starts with our gas, right? And that is chemical energy. So in your grade 11 and 12 chemistry courses, you'll talk about chemical energy and how much energy is contained in, say, a liter of gasoline. So the gas energy, what does it do? It becomes heat energy, all right, because it drives the pistons. So we have combustion. So we get heat energy. And I'm going to simplify this for people who are following along. Yeah, it's a lot more complicated, but this is just, remember, an introduction to the particular topic. So it goes from gas, we get combustion. Let's jump to the pistons moving. So inside the car engine, the pistons move. And now we start getting into a little bit of repetition because it's going to be mechanical energy. So what does that do? The pistons move, the drive shaft. And I'm going to skip transmission. I'm not going to go into all of them here. Again, mechanical energy. So it's changing its form. And then I'm going to jump all the way to the wheels. So what do the wheels do now? They start moving the car, so now we're into kinetic energy. So again, it's just a simplification at this point because we're just being introduced to this topic. And for people that haven't taken auto shop or aren't familiar with vehicles, that's a very simplified version of what happens. It starts with gas, with our chemical energy, and it ends, the end result, or what we want, is kinetic energy, that's motion. So what we're looking at, we're going to be analyzing some of these transfers, again, in its most simple form, since this is introductory material, and you get a feel for how that energy transfer occurs. So what are the requirements for work? What are the requirements for work? There are three separate requirements here. First requirement is displacement occurs. So displacement occurs. So that means that an object has moved from point A to point B. Okay? The second one, a force is applied. So that means that there was an applied force added. And the third and most important one, because this is going to come up and they're going to try to trick you in some of the homework, and I'm going to put a couple multiple choice questions on the assessment to challenge you a little bit on this, but the displacement and force must be in the same direction. Displacement and force must be in the same direction. Same direction. Okay, so underline must. So that means if an object moves from A to B, applied force had to be in that direction. So let's take one of the examples I always have in class. I always get a student to come up and hold a bunch of books. So here's my student, and I pile books on and tell them they can't move their arm. They have to hold those books right where they are. So the question I always ask, is work being done? So while I'm doing this, the person will be sweating and grunting and getting a really sore arm as they try to make sure the books are stationary. So the question is work being done? And the answer is no. As much effort that person is putting into holding those books up, they are doing absolutely no work. Why is this? No displacement. Are they applying a force? Yes. But if they don't have a displacement, if one of those three criteria above fail, then no work is being done. Similarly, what about the person walking down the hall? Don't laugh at my people. And you're carrying a backpack. Okay? Are you working when you walk down the hall with the backpack? If we look at the free body diagram, for the backpack, what forces are acting on the backpack? Well, you have a force due to gravity. You have the force of your shoulders. I guess we'll go FS for that one, force of shoulders. Holding the backpack up. Okay, so is there a force being applied? Yes, there is. Perfect. What about your displacement? Displacement is left or right, depending on which way you're heading. So is work done, or work being done? So is work being done? Is the question again. The answer again is no. The force, which is upward, is not in the same direction as displacement. So force and displacement, not in the same direction. So therefore it fails. So as long as you have one of these three criteria up here, if one of these three criteria fail, then no work is being done. So you need to keep that in mind when you're asking that question, is work being done? So a worker pushes a 20 kilogram box for 5 meters with 150 newtons. How much work is done? Well, I'm going to have to actually go back a slide, I guess, and I need to give you the formula then. So off to the side here, work, which is equal to, if it's mechanical energy, remember I just said in the previous slide, they're the same thing. It's equal to force multiplied by your displacement. So there's your formula. If the force is applied at an angle, then it is the magnitude of the force multiplied by displacement cos theta. All right, so the challenge with this unit is keeping your formula straight. So work is known as mechanical energy. It's calculated with force times displacement. If the force and displacement are not in the same direction, you have to find the component. And when we get to an example like that, I'll show you. You have to calculate the component. So there is the formula, which allows us to answer this question. If the worker pushes the 20 kilogram box, so I'll just draw a picture, moves at 5 meters, 150 newtons, so it doesn't say direction, so we can assume it's in the same direction. How much work is done? Well, work is equal to force multiplied by displacement. So that means we would have 150 multiplied by 5, and you'd get 750 joules of energy. Joules of energy. So work has the units of joules, which we simplify to J. And what does a joule equal? If we look at the formula up here, force, which is newtons, multiplied by a measurement of meters. So a joule is a newton meter is its base unit. Okay, so there we are. A child pushes a toy tractor 5 meters right with a force of 10 newtons right. How much work is done? Both are to the right, so it's a simple example again. It's just emphasizing it has to be in the same direction. We can use this formula right here. Force of 10 newtons, 5 meters in distance, so it's 50 joules of energy. So therefore, 50 joules of work, or mechanical energy, is done. Okay, we'll cut this video off here and finish the lesson up in the next one.